Hello friends and welcome to this video. We are at the conclusion stage to the chapter number 6 that it is titled Adaptive Filters. The various types of the concepts we have learned for the design of the adaptive filters, either it is of the FIR type or the IIR type here. And so far we are completed with the previous 4 videos where the practice of different problems were taken, and in those particular problems we have addressed the steepest descent algorithm, the LMS algorithm applied for accomplishment of the task here. Now we are going to have one more problem, that is why here it is titled problem 5 adaptive filters, and in this problem we are going to have design of the LMS algorithm based adaptive linear type of the predictor here. So let us see what is the exact problem statement and how do we solve it. So let us begin with the topic. So here we start with our topic that is titled problem 5 adaptive filters. We have been provided the problem statement. It is the first three autocorrelations of a process x of n are given to us. Those are represented as small r suffix x of 0, that is equal to the value 1, rx of 1 is equal to 0.5, and rx of 2 is equal to 0.5 again. We have been asked to design a two coefficient LMS adaptive linear predictor for x of n that has a misadjustment that has been denoted by capital M is equal to 0.05, and the question continues to ask us to find the steady state mean square error. So this is the complete problem statement, short and simple. Now if you look at the given information, see, we have to deal with a discrete time random process which is denoted by x of n as usual, and the information regarding the autocorrelation sequence is provided to us. The three samples we have been provided. So this is just the formation of the autocorrelation sequence. So we have the 0th value, first value, and the second value from the sequence. These are 1, 0.5, 0.5 here. So with the help of the misadjustment denoted by capital M, we have to design a two coefficient LMS algorithm based adaptive linear predictor for this input discrete time random sequence x of n here. So this is the first part, and in the second part we have to also find the steady state mean square error. So let us start with determining the answer for first part, as I say, design of the two coefficient LMS adaptive linear predictor. So here we are going to make the use of a formulation for the misadjustment here. See, the misadjustment, as we have seen while discussing the topic thereupon, the design of the LMS based filters here, capital M can be equal to alpha times TR of capital Rx divided by 2 minus alpha times TR of capital Rx. So capital R suffix x is the autocorrelation matrix associated to the discrete time random process denoted by x of n here. So therefore, from this relation, if we need to isolate alpha, first of all what we shall do, the denominator of the right hand side we multiply to the left hand side here. So we transfer it to the another side. So therefore we get the equation with the form twice capital M minus alpha capital M TR of the autocorrelation matrix capital Rx. This will be equal to the right hand side left with alpha multiplied by TR of Rx here. So when we try to isolate alpha only, we get alpha is equal to twice capital M divided by 1 plus capital M multiplied by TR of Rx here. Now in the given problem statement we have the value of misadjustment capital M, that is equal to 0.05, and we know the TR of the autocorrelation matrix capital Rx will be equal to 2 times Rx of 0. So Rx of 0 is equal to 1. When we multiply it with the value 2, it will be simply 2. So TR of Rx is equal to 2. The misadjustment M is equal to 0.05. So this we can put into the equation of alpha. So twice M divided by 1 plus M, the bracket multiplied to TR of Rx. So all the unknown parameters, those we find on the RHS, are now known. So substitution of the values results into the computation of alpha to be equal to 1 upon 21 here. So using the alpha value, we can write the LMS update equation. The LMS update equation is the relationship with W suffix n plus 1 and W suffix n. So here we have on the LHS W suffix n plus 1, that is equal to W suffix n, added by the value of alpha, that it is 1 upon 21, multiplied to the error signal E of n between the desired signal and the related signal here, in multiplication to the related input signal, that it is x of n here. So this is what the solution. We were asked to design a two coefficient LMS adaptive linear predictor for the given discrete time random process x of n. So here it is the answer. You can outline this. Now the second part is to find the steady state mean square error. See, the steady state mean square error can be denoted as xi as a function of infinity, which is xi minimum added with xi ex as a function of infinity. So here we can have it to the form xi minimum multiplied to the square bracket, that is having 1 added to xi ex as a function of infinity divided by xi minimum here. So this is equal to also 1 plus m, the misadjustment multiplied to the xi minimum here. So if you put the value of the misadjustment, that is equal to 0.05, added to 1, it will be 1.05 multiplied to the xi minimum here. Now since we know the computation of xi minimum, so xi is representing here the mean square error. The minimum value can be computed with Rx of 0 minus W of 1 multiplied to Rx of 1 minus W of 2 multiplied to Rx of 2. So here we can have the substitution of values into the matrix form. We can have the first square matrix having the first row elements 1, 0.5, the second row elements 0.5, 1. This 2 by 2 order matrix is multiplied to the matrix of the weights W of 1, W of 2 in a column matrix form, and this is equal to the column matrix again with the value 0.5, 0.5 in the two rows here. So here with the values of W of 1, W of 2 to be equal to 1 by 3 substituted, and the above equation we have xi minimum is equal to 1 minus 1 by 3 into 1 by 2 minus 1 by 3 into 1 by 2. So this is supposed to result into the value 2 by 3 here. So here we have xi of infinity, that is equal to 2 by 3 multiplied by 1.05. So this is supposed to result into the value 0.7. So this should not be the minus sign, this should be the equal to sign here, and this is what the required answer. The question part was find the steady state mean square error, and this is the value of steady state mean square error, that is equal to 0.7. So this way we are completed with solving the problem number 5 based on to the understanding of the LMS based adaptive linear predictor here. Now the next lecture will be the last lecture for the chapter number 6 titled as adaptive filters, and it will be a last problem. So the title of the topic, it will be problem number 6, adaptive filters. Thank you.